Okay, a very good afternoon to everyone. Our speaker for day 3, session 6 is Dr. Jitendra Singh, Principal Scientist, CSIR CIRI, renowned for researcher and academics in MEMS based devices and piezoelectric. Now, I would like to request FDP coordinator Mr. Rajesh Singh Sekhawat to welcome our distinguished speaker with the bouquet. Dr. Singh received his MTech degree from IIT Delhi in 2006 and PhD from the Sensor and Nanotechnology Group CSIR CD Pilani in 2016. Earlier, he was also employed in Central Research Laboratory and Bharat Electronics, Bangalore, India during 2006 and 2010. As a part of joint research project BEL IIC Bangalore, he was also working at a material research center IIC Bangalore. He is currently principal scientist at CSIR Siri Pilani. He has visited several countries such as Germany, Japan, Singapore. He is a member of various scientific societies in India. He has hands-on training experience on design, fabrication, and characterization of micro-nano electronic (MEMS) devices. His research interests include piezoelectric, ferroelectric, and magnetoelectrics, thin film based micro-nano electronic devices. He has completed a total of 11 projects funded by different government firms worth of crores. Dr. Singh has published more than 130 papers in international and national reputed journals and conferences with total citation of 927. So without further delay, let us warmly welcome to the stage Dr. Jitendra Singh, who will be sharing his expertise. Sir.
Mhm. Good afternoon. So I think it is after lunch session.
Yes, sir. It is
So all are ready to listen me.
It is. If we listen your voice, maybe we are like in a different mode.
Yeah. So wake up and we'll learn the semiconductors, microsystems, design, fabrication. Correct. Semiconductor itself is a very interesting word, right? And you are doing the great thing that semiconductor excellence now government is planning. It is in the right directions. We all are going. So this comes in mind from last 20 years I am in doing the semiconductors. So I'll share what I'm doing and how we are doing. The things we'll discuss. Second thing is the microsystems. Micro means their size is micron size. They can be systems or devices, right? So we learn the design, how we do it, we fabricate it, we characterize it, we package it, and we deliver it. So we do end-to-end work. So Siri, I think many speakers came here and you know very well about Siri. It is your neighboring lab. So, and it is a national lab, part of CSIR. It's the green campus. And CSIR has 38 labs across the country and Siri Pilani is one of them. It is very old lab, established in 1953. So we do the research work mainly on the electronics devices. CSIR has the labs based on each theme. Our theme is electronics, which is the best theme I feel. And I'm myself working in the semiconductor devices this group. We have various other research areas here in SERI like the intelligent systems group, packagings groups, semiconductor device design groups, fabrication group, then the societal electronics group, vacuum microwave tubes groups, and the vacuum electron devices development groups. So today we'll talk on the our objectives, what we are doing here. Other thing is the Indian semiconductor mission. Government of India is doing ISM and there is a big plan for that. We'll discuss all the aspects like the commercial aspect of it, why we should do the semiconductors. We'll learn the microsystems. MEMS stand for the micro electromechanical systems. So micro means they are of micron size, electro means electronics and electrical part will be there, then mechanical part will be there, and complete it is called the microsystems. So it is a full term MEMS. In the worldwide it is called MEMS, but especially in the Europe it is called the microsystems. So it is the terminology. We'll see the trends, which direction semiconductors are going and what are the devices being developed. The micro cantilever based sensor, semiconductor sensor, magnetic sensor, mass sensor, some of the filters, trends we'll see and discuss. If you'll see the full world economy, how big the semiconductor economy is, means it is part of our daily life. But if you'll see the global, how much the big economy it is. Our daily life is affected by semiconductors. We interact with the things, even it is semiconductors. Our computer is semiconductors, mobile is semiconductors. So it is a very big economy. If it's 21, you will see it is 527 billion US dollars. And 22, it is, if you'll see, it is 573. It is increasing. And if you'll convert into $1 billion into rupees, this world economy of semiconductor is 47 lakhs crore rupees. You can imagine how big economy it is. 47 lakh crore rupees. And it is growing with the compound annual growth rate of 12.2%, and expected that by 2029 it will be 1380 US billion dollars. So it is the biggest money engine people have made, but in India we are lagging in it. Now we have to make the ecosystem, how we can strengthen it and how we can move forward. It is the Asia Pacific semiconductor markets. During the COVID time, 1920, it was slowed down, but again it is increasing now, 23, and it is expected that by 29 it will be again will reach very high. So there is demand, but if you see the Indian content supply is not there. We all based on the imports. How we can substitute it? How we can generate our own semiconductors? Even a single chip we are not manufacturing in India, we are importing. So we'll see all these aspects. If we'll see a global semiconductor market share by application, like networking and communication is the biggest segments devices are used. Then the data processing, smaller, then the industrial, consumer electronics, automotives, governments. Even if we'll see in India, we don't have any big consumer electronics company. All are companies, foreign companies. So it is the time, high time for India to develop the semiconductors and come in this market. If you'll see a market share, it is nearly 23 years back, 2000 if you'll see. It is blue stand for the US, this violet stands for the Japan, Europe, this one, and this is South Korea, then China and Taiwan. Okay, so if we'll see it, these are the 1, 2, 3, 4, 5, 6 countries, dominant countries. So nearly 20 years back, dominant was from the US side. And then the Japan was doing, then the Europe was doing, and then the South Korea was doing, then the Taiwan was doing, but China was nowhere 23 years back. But if you'll see now, 25, the US is decreasing its growth rate in the semiconductors, but the Japan also decreasing. But the one more player has started to come here. It is small, you can see this China, okay? And you see started from here, now it is reaching here, then 5% in 15, then 9%, then 16%, then the 23%. It is capturing the full market. Now there was news that US has banned the semiconductor supplies from the China, and it will not supply to any very high-end equipments to China. There was news. Because there was threat to the US that its share is decreasing in the country's share and the China is grabbing the market. So, and India do not exist anywhere in these because we are good in services, but we are not good in semiconductors. So it is a India has to grow in the semiconductor side and it has to make its footprints. So now government is thinking about it and we have to contribute in this direction. The big threat was came in the COVID times. There was everything was locked down and supplies was coming from the China or Taiwan. They were also stopped down because there were no manpower working. Then all the automobiles they need the chips and they all supplies was broke down. They meet with the Prime Minister and they ask India can do the semiconductors. And if we can have the indigenous development, we can do great things in this direction. Then the government make a plan. And if you see the ministers are this Chandrasekhar and the Minister of Electronics and Technology and the other Aswini Vaishnaw, both are from the technology background. They are working on it. So it is from the government side, it is a good initiative in the semiconductors and our lab theme is semiconductors. So it is very much matching with semiconductor industry value added by the activity and region in the, and now I'm commercial part I'm taking because you should know why it is important and where we are now in the India. So it is a very important thing. So if you'll see the 21, EDA means electronic design and automation and the core intellectual properties. So it is the main part of it and US was dominant in the 72% work was doing, other was 20% was Europe and other countries were doing. So major player is the US, still it is a major player. Other is the design part, the logic memories, hybrid fablites. So it is the design part and design subtotal if we'll do 49% is the nearly 50% is part of the US. Other like Europe, China, Korea, Japan and Taiwan they are doing. So still the major player is the US. Other part if you'll see the what we need in the semiconductors, design we are done, then we need the equipments. Equipments are very costly here. Maybe one equipment can cost more than 10 crores. Even we have in the series, the equipment cost is more than 10 crores. Okay. How many of you have seen the semiconductors by eyes that it is semiconductor? What product you have seen? Silicon chips you have seen. Wafers you have seen. All you have seen. Good. So one wafer can have how many devices?
It depends on the size of the wafer.
Wafer can be of 3 inch, wafer can be of 4 inch. Right. But in series we process 3-inch wafers or 4-inch wafers, and now we are planning for the 6-inch wafers. So one sample piece I bring for you. So it is one piece of 3-inch wafers, right? And if you'll see this one line, horizontal line, it is the 15 chips. In perpendicular, it is a 15 chips. So 15 by 15, 225. Okay, so one wafer has 225 devices. Only 3 inches. So if it is 6 inch, then I will have 1000 devices. Those who have not seen can see the semiconductor wafers. So it is the market share.
Do not open, but it's like just see, because it may be contamination may be there. So just see backside, it is visible. ज़्यादा अच्छे से backside को दिखा रही है.
Hi, you can pass on. So, other is the semiconductor equipments we were talking. So these are very costly items. Cost in the crores. Other is the materials. Material, silicon, abundant material available in the nature. But in the purity like this wafer form, we don't have. It is the highest purity of silicon, 99.99% plus single crystal. We need a single crystal silicon, right? Single crystal. Why single crystal needed? Can work with the simple crystals, right? We need single crystal silicon. I think all from the electrical engineering backgrounds, right?
Mix in computer science,
Computer science. So a single crystal, why we need single crystal wafers? It is a single crystal wafer. Why we need single crystal?
like a growth of other material is easy on a single crystal.
Yeah, it is one point. Other thing is the on single crystal we can do various processes which are possible. There are no defect in the single crystal, therefore single crystal required. Right? Yeah. Other thing is that we can grow a high quality silicon dioxide on it. Especially in Rajasthan, we have abundant silicon dioxide. Is all silica, but in the purity form, we don't have. We don't have those processes, those technology which can make convert this into useful form of the wafers. So those technology barriers we have. Therefore, we are lacking. Even the silicon, this wafer production plant, we don't have. Yeah, there are Europe or US, we buy it, these wafers. So one wafer costs nearly 3000 rupees.
It depends on the material also.
Material also, like silicon wafer, 2-inch cost nearly 2000 rupees, 3-inch cost 3000 rupees. Then we'll process it.
But processing method is much more costlier than a wafer.
Right. 3000 wafer rupees cost, but any process can come on this that can have 10,000 or 20,000 rupees. Yes. Like if I want to do a platinum deposition, that will cost 47,000 rupees.
Yes, because it is a centralized facilities available in Siri. If you want to perform any kind of process, so individual cost is like very huge.
Yeah. So these are the big players, and overall if you'll see, the US is a dominant player, then the Europe, then the China is coming, then the South Korea. Taiwan is a hub of these semiconductors because of their policies and the things. If you'll see the end users, we use semiconductors in the computers, we use in our communication devices like our mobile phones, we use in our cars, because all the artificial intelligence is possible using semiconductors. We use in the consumer electronics, industrial, like we use, then the government also one of the user, and it is the total value of it. So government portion is less, but computer and the communication, these are the major things we are the consuming. If you see the market segment by the devices, logic and the memories are the biggest segment. Then comes the analog. Optoelectronics device segment is small. The sensors is emerging, required everywhere. This segment is increasing now. Then the discrete devices comes. So it is the shows the market segment of the semiconductor sales in 2021. Now let us see how big is the Indian market. We have seen the global market, how big consumer we are of the electronics and semiconductors. If you see, our budget is the 24 billion, 2 lakh crore rupees. Okay, and we are importing semiconductors also, we are importing petroleum products also, diesel and the petrols. So if we'll compare the petrol, diesel we are importing, so it is we are importing petrol, diesel, these of nearly 12 lakh crore rupees currently, and semiconductor we are importing of 2 lakh crore rupees. So it is only 6 times. So if we can make the semiconductor, we can think that we are making a petroleum products. Yeah, we have to make our economy strong. So one way can be we can make our Indian semiconductors this technology we can develop, and we can, if we can substitute the import of this, we can compensate with the petroleum. Petroleum we cannot do because we don't have those resources. But yeah, natural resources. But semiconductor we can do. So that can be a big thing. So India is the 1% of the global trade in semiconductor, very small part. But if you see by population or by other things, we are a big part. But here only semiconductor we are doing 1%. So India has a role to increase now. There was policies were not proper from the government side, so it was lagging. Now we'll see the semiconductor chips. What the chips are? Chips are made of the semiconductors, silicon or germanium or gallium arsenide or silicon carbide or gallium nitride. These will be the materials of choice. And other question is, what is the biggest invention till date? What do you think? आज तक की सबसे बड़ी खोज transistor is the biggest thing. Yes. In today's time, it is means if you see the last 100 years, the biggest invention is the transistor. But if you see the old times, the biggest invention was the your पहिए का आविष्कार, पहिए का आविष्कार, पहिया और आग जो फायर है, क्योंकि उससे उसमें पहिए से तो उसको मूवमेंट मिल गया, and fire they were able to cook their foods. So earlier invention was the biggest was the wheel and the fire. But the current time, modern time, the biggest invention is the semiconductor, transistor. Transistor, everything has changed. If you see the old days, transistor, they were using the vacuum tubes, amplification, where they were doing with the vacuum tubes. Those were big. Yeah, we cannot make them small. But now this transistor has made this so small, 7 nanometer, or there. I think soon they will reach to the atomic scale. No further miniaturization possible. So semiconductors are the materials. Significance of semiconductor, they are the basic building blocks, and they serve the heart, brains of the modern electronics and information and the communication technology projects. These chips are now an integral part of the automobiles, your gadgets, medical devices, and during the COVID-19, no, there was pressure came on the semiconductor industry because everything was halted, and Indian this automobile sectors was down because there was no supply of the chips. Then they decided that they will go for the semiconductors and display devices. So India started a mission called the Indian Semiconductor Mission, or ISM. Its vision is They want to build a semiconductor and the display design and the innovation ecosystem to enable India emergence as a global hub for the electronics manufacturing and design in a focused and a comprehensive manner. So they want to make the ecosystem of it. They want to first they want to start with the display devices because that is the easy task they can do. Then they will go for the fab like processes. Display means whatever the screens and so those like our on this mobile phone screens, laptop screens, it is the easy part of it. Then the display and the manufacturing semiconductor design ecosystem they want to develop, and the intellectual properties, like you have done the innovations. So if you'll see the semiconductor companies, their strength is the IP, intellectual properties. Those who have the more IPs, they are more strong. And if you see the US and other countries, their IP policy is very strong. If somebody is breaking the IPs, they will put in the jails. There's very tight laws there. But India, we are not so focusing on the IPs. But IPs is the best thing India is now pushing the things. And in Syria also, there is pressure from the government side that the scientists should do the more IPs now to make an ecosystem. Then the transfer of technologies. They will give the incentive to the concerned peoples who will do the TOT. Okay.
Transfer of technology to the industry.
To the industries, so that ecosystem will develop. And further there are, we have academics, we have pool of talents, and like CSIR is the facilities are there. So government is trying, there is partnership between the your colleges, universities and the your academic research and the institutions, so that they can make an ecosystem. So basically the government is pushing for the semiconductor fab. If somebody will put in the policies that if somebody will put a fab in India, they will support 50% part of it. Subsidy they will give. Total cost, half of it government will provide. It's called the PLI scheme, Production Link Incentives. Display fabs also they will support 50%. Compound semiconductor, which composed of your gallium nitride, gallium arsenide, silicon carbides, compound semiconductors. So it is the they will support. And the design linked incentives means the design will do in the India. That also will be supported by the governments. All the software companies, India is doing well in the software, but we don't have Indian softwares. We work for others who outsource the things, our manpower utilized for it, and it goes all the things that they sell the softwares. We are not selling the softwares. They are making the money out of it.
We are just an
We are getting employment, that's all. Then the one is the compound semiconductor, silicon photonic sensor fab and the discrete semiconductor fab, which is the area of interest of the our lab, matching with the MEMS and the sensors lab. So this is also one of the initiative of the governments, and they will support the 50% of the expenditures. So this I was explaining as a part of the government policy. What is the significance of the semiconductors? So we discussed that it is the part of the all our aerospace or automobiles or communications or clean energy. And you can see these two gentlemen, they are wearing the clean room garments. So even one particle is very important, the clean room. One particle can affect my process and can destroy my process. So cleanliness is very important, and human is the biggest source of these particles generations. So clean room like class 1, class 100, class 1000, class 10,000, those are the categories of the rooms we have to work in that. So government in December 2 years back, the government has given a 76,000 crore rupees PLI scheme to boost these semiconductors. Who will produce this? They will come in this category and government will give the subsidy. It is the sections wafers and it is probe using a your in electrodes to make the signal out. So it is the testing process is going on the sections wafers. We'll see the semiconductor clean rooms and some process is doing. So we know that semiconductors are the modern age and every part of it is affected by the semiconductors. These chips are drivers for the information communication and technologies, and they are the critical infrastructure such as the communication, power transmission and security applications. The semiconductors are everywhere. There are many, not many countries which are advanced in this. US, Taiwan, South Korea, Japan, and Germany, and some European countries are the dominant in this market. India still has to make the footprint in this. We discussed that currently the it is Indian market is $100 billion, and it is now $24 billion, but 25 it will be 100, so increasing with the very fast speed. And India also launched a scheme called the Promotion for Manufacturing of Electronic Component and Semiconductors for the manufacturing, and it is called a design linked incentives also for the 20 domestic companies who will develop the semiconductor design, and government will give them the 1500 crore rupees in the next 5 years. There are some plans from the government side. So India is a big consumer of electronics, but not a producer of the semiconductors, electronics. Why we are lacking? What are the reasons behind it? Why are we are not so good in semiconductors? One thing is the high investments required. It is if semiconductor fab, if you want to establish, $1 billion investments required. And our businessmen who has the money don't want to invest for that, because there are many reasons for it. The return of investment, ROI, it will take time. So they don't want to take a risk. Other thing is the technology change day by day. Today is the 22 nanometer, tomorrow will come the 7 nanometers, then the full fab will change. So it is difficult for them to maintain it. So one is the high investment required, and it is a risky work, and nobody want to put their hands in that. And government now the scheme is there, but even with the 50% support in the incentives, no players are coming to make the fab. Only
50% is also a very huge amount.
Huge amount. Only the Micron has come forward, and they will not do the front end, they will do the back end technology. Front end means full fab fabrication, but back end means chips will come from the abroad and they will do the packaging part, that called the back end. So minimum support from the government, so lack of fabrication capabilities. Fabrication means we don't have the fabs here, only one fab is there, that is ISRO fab. They are using for their own applications. So and the equipments required for this, It is in SCL Semiconductor Complex Limited. One fab we have in India, that is SCL ISR Lab, Semiconductor Complex Limited, SCL called. So it is a lack of fabrication capability. Plus the machines required, we do not produce in India. Those are also all imported. So that is one reason. And other thing is the extremely expensive fab setup. The clean room class 1, class 100, class 1000, and maintenance of those very costly process. Other is the resource inefficient. We need a very clean water, very stable power supplies, highly skilled manpower. Those things are also missing. So it is also a one processed, I think the 12-inch wafers, the persons are doing the inspection. What can be the way forward? India need a chair for the discussion with the countries, the developed countries like we discussed, so that India can be part of that forum and can discuss their semiconductor policies and issues, because somewhere we need the guidance, right? So then India can be a good player in the directions. So discussions are going on. I was part of the meeting where we invited some of the our persons, Indian peoples who are doing very good semiconductor works in the other foundries in the US. So we invited them for a discussion. Sufficient fiscal support for all the elements. Self-reliance we have to make, means we have to make a ecosystem for it so that we can produce the things. High investments are required here, so we have to make our businessmen ready for that, and so that they can produce the involving, they can, it will take time for the them to make the return of investment. It will take the time, and we can make a important component by the these have the important components are the hardware, which we see the silicon wafers, design of it, and the fabrications. So we have to make strong ourselves in all three, then it is possible we can go forward. The main pillars of these are the, we should have a free and open markets, like we produce in India and we can sell it to the other countries. We have a good support for the intellectual property protection, support I made sub patents. So government should provide the full support so that we can, our rights should be protected. There should be supply chain integrations. Whatever I produce, it should be go to the end users. So that should be maintained to make a consistent progress. Other is the, we have to make R&D, top class R&D in the semiconductors, so that we can come with the in the line with the top players. Trained manpower or the workforce developments, we have to train all peoples in that directions who can make the semiconductor research, design and manufacturing easy, and market-based government incentives should be supported by the government. Now we'll see the semiconductor. One of the application daily we use is the smartphones. So semiconductors, one part we study, the one is the sensors and the MEMS devices. That is one of the component we work here. So now we'll discuss the work we are doing in the Sri Pilani on the sensors and the actuators. Okay, if you'll see our smartphones, how many are the microsystems or MEMS part inside our pocket? There are many. In our these smartphones, there are microphones. What they do?
Just the voice transfer.
Convert. One story I want to tell you, that semiconductor, why important for us also. There was one program from the ISRO. They are launching these PSLVs, right? So PSLVs, they use these microphones or acoustic sensors, right? They need for the, like our balance, we have two acoustic sensors here, okay, that make our balance. Similarly, if the flight PSLV rocket goes, who will make their balance? They need the sound sensor or acoustic sensors. So the ISRO was importing from somewhere, and they asked the declaration where you will make the end use of it. We told that we'll make in the PSLVs. They denied. If we'll make the space applications or defense applications, they will not supply. Yeah. Then the threat came that if they will not supply, then we have to develop it. Then these microphones or acoustic sensors for ISRO we developed in Sri Pilani. That was my first project in Sri Pilani I done. And we developed these components not for smartphone, but for the PSLV rockets. Yeah. We developed the materials and it was actually utilized in the PSLV rockets. We supplied chips to them and they packaged it. If you'll see our smart, so therefore the semiconductors we have to develop in India, because end use we have to tell them, then they will deny us. So therefore we need to develop our technologies to make us Atmanirbhar. So microphones is one of part of it. Our voice is converted into mechanical to electrical signal. Magnetometers are there, proximity sensors are there, gyroscopes are there. See, your screen is tilted. Yeah, those I think is the gyroscope, humidity sensors, force sensor, gas sensor, camera, light sensor, temperature, and I think many more will join this family. Our biological things, this will add up to this.
Like heart rates and that.
Yeah, pulse and the things. I think will soon will join, and soon app will come inside and it will be your doctor, right? So if we'll see this PCB of this, your microphone is here, which is able to listen our voice. Your accelerometer, gyroscope, electronic compass, pressure sensors are there. The frequency signals coming, like now it is talking of the 5G communications. 5G communication means 3.83 gigahertz frequencies. So filter those 3.83 gigahertz frequency, we need the filters. These can be bulk acoustic wave filters or duplexers or oscillators. So those are all based on the microsystem technologies, semiconductor technologies. We do the development of these filters and resonators we'll discuss today. Also the MEMS micro mirrors, CMOS image sensors, autofocus actuators. So here in series we are doing one project on the bulk acoustic wave filters. These are the piezoelectric waves based resonators and filters. Today we'll discuss. Why these microsystems or MEMS are important? It is a trend and it is a requirement also to make a small size electrical components, right? You see this microphone, less than 1 mm size, okay? Gyroscopes, energy harvester, motor, com drive, resonators. So with these small products, we have the reduced cost because we've seen these wafers. In one wafer, we can make the 1,000 devices. Single process we produce 1,000 devices in a wafer. Otherwise, we have to produce one device, the next device, the next device, 1,000 times we have to do. But here, once we're done. So it is a cost reduction, improved product and building materials, ease of transportation, because if small size, I can transport it very easily. Power also consume very less, benefit, high precision and small scale devices, and silicon based processes available, wide range of these sensors, actuators and resonator filters can be made using MEMS. Let us see what are the dimensions. Now it was a COVID time, right? What is the size of the coronavirus? Did you ever think of? उसने हमको नैनोमीटर साइज की छोटी चीज ने हमको परेशान कर दिया था, राइट? So let us think, humans are size in the meters, okay? Our hands in the centimeters. What is the diameter of our hair? One hair, single hair. It is nearly 100 to 50 micrometer range, okay? RBC of less than 10 micron and the E. coli is less than 1 micron is the area called the MEMS or microsystems. 1 millimeter to the 100 nanometer is the MEMS microsystems and the MEMS. This region is called. Your virus is less than the 100 nanometers. That was the virus. And then if the feature size or the less than the 100 nanometer, then the nanotechnology area comes where the nano pictures, nano structures or nano features will play into the role and make a significant change in the device configuration or their behavior. So it is a very interesting area. Because if any object or any particles or any layer or any system size comes below the 100 nanometers, its new behavior will appear. And people study this domain is called the nanotechnology. So here I want to say that the miniaturization is the driving force. I want to make a small size devices as small as possible, maintaining the same performance. The MEMS, we do the design, we have the various tools in Siri also. We use ANSYS softwares, COMSOL multiphases, Coventor, Sugar, IntelliShoots. And some of for the creating geometries, we use MathCAD, AutoCAD, or layout editors. Some of the resonators and filters, MEMS based, microsystem based, we do the design work using the advanced design system, ADS called. So it is a advanced electronic design automation software for the RF, micro and communication, the high speed signal digital applications. Micro Office also one of them, Cadence, HFSS, high frequency structure simulators, electronics workbench, SPICE, VSDL, LTM, NSOF Designer, Microsoft. So the various tools as per your requirement you can use. So technology to make a small size device is called the MEMS or microsystem technology. Here we have a small size component which performance is very high and provide me the optimal performance. We discussed that the various actuators, sensors, resonators, filters, gyroscopes, hearing aids, sonars, transformers, accelerations, and has the various applications in the biocides or acoustics or inertial sensor, chemicals. Chemicals, we developed one of the formalin sensor here. We'll discuss microfluidics, optical sensors, various applications. If we'll see the definitions of it, we'll define all the terms like the microsensors, sensor which realize using a microfabrication technologies or processing is called the microsensor. What is the difference between the sensor and the actuators? My nose is a sensor or actuator. Smell. Sensor or actuator? Sensor. But actuators, give one example of actuator.
We can convert the one energy into the
That also nose doing this work. It is smelling. It's one form of energy converting into other. But what actuator does? Actuator, one example. It is, I'm grabbing it. It's doing actuation, right? Actuation. Task perform. I have given this energy to this hand, it is capturing, it is actuation. In actuation, I will provide energy and it will do some function. It will actuate, right? In sensor, it will do the function, it will give me the signal output. But in actuator, I'll give the signal, it will do some actuation or action. So that is the basic difference. So microactuators are realized using the microfabrication technologies. Microsystem, complete system realized with the microfabrication technologies. Means we know the terms, the micro electromechanical system. These are the small size systems. Various applications, they have the mobile devices or IoT, automotive, domestics or entertainments. And they have the various applications affecting our daily lives. The consumable electronics, the shipments of the various are very high, like the millions of the units wearable devices, and they are in the market. If we'll see our car also, there are various sensors. Why these are important? Now there was a project in the series that this when we are driving a car, we don't know what is the tire pressure. But there is one project, there will be one sensor which will monitor the tire pressure, and it will give a signal through the RF mechanism, and it will come on your dashboard. So in the coming cars, there will be, you can monitor all your 4 tires pressure on the dashboard.
It is already in some cars.
Some cars, high-end cars, it is there. It is there.
But sometimes it happens that when we drive a car, and pressure may be instantly increases.
Yeah.
If you drive a car on highway, that time it will be a problem for the tires.
Yeah.
That's mostly required the tire sensors.
Tire pressure sensor. So it was from the JK side, they need the tire pressure sensors. We have the brake pressure sensor control, accelerometer for the suspension control, mass airflow sensors, air conditioning sensor, silicon sensors, and the fuel injections for the controlled fuel, accelerometer for the air bag deployments, microphone for the noise cancellations. So sensors based on semiconductors need everywhere. Automation, there is high need of it. So if we'll see the top players in the semiconductors, what are the top players who make the top class devices and the supply? Broadcom is one of them. Our smartphone, like it utilizes filters or resonators or oscillators or switches, all produced by the Broadcom. We know the Bosch companies, ST Microelectronics, Texas, Coro, HP, NXP, and there are many companies who are dominant in this field. But our footprint is not there. No Indian companies produce any sensors or electronics component. Still, we have to go in this direction, and we have to join hands with that. MEMS packaging. We'll see it, the radio frequency MEMS, acoustic and ultrasonic MEMS, environmental sensors, optical MEMS, inertial sensors. MEMS is the increasing with the CAGR of the 16.7%, and it is continuously increasing. Also the microphone we discussed, there are the unit supplies for this, and if you see the 2022, the condenser ECR condenser microphone is reducing, and the other part is the increase. This part is the increasing, but this one ECM volume is decreasing. If you see how does the MEMS microstructure look. It is a once micro electromechanical resonator from the ST Microelectronics. It is a very complicated devices. You see the comb-like structures, gap is maintained between them. When the structure will move, one is the fixed and other is moving. So due to the movement, some capacitance will change, will measure the electrical signal. So it is due to the linear movement. If the rotational movement is there, these kind of mobile parts can be there. So these are by design very complicated structures, very difficult to design, very difficult to realize. So it is a highly expertise areas. If you see the structures, you see the floating plates. one plate of the made of the silicon dioxide or nitride is just floating on the and over a cavity. It is a one bridge made. You know the length of this bridge, maybe 100 micron. One hair, like one hair thick, this much. It's very difficult to realize. Cantilever anchored on hair and doing some action when it is actuated or some for the sensing signal. The crossbeam, spiral made on it, springs. So these are the microsystem devices made for the some special applications. Materials we use, silicon is a major material or your microelectronics industry based on it, and similarly the MEMS industry also based on the silicons. Anisotropic semiconductor crystals are made, polysilicon mostly for the semiconductor material, for the piezo resistors, silicon dioxide, excellent thermal and electrical insulators, therefore it is used. Silicon nitride has the thermal conductivity very low, and in this wafer we use this silicon nitride. Aluminium, very good electrical conductors. Copper, excellent electrical conductors. Gold and platinum, excellent conductors. Various polymers also used there as per the requirement of the sensor. So if you'll see the major materials like silicon, carbon, silicon nitride, iron, tungsten, steel, molybdenum, aluminium. The major parameter we look for practical applications, their strength, yield strength, Knoop hardness, Young's modulus, density, thermal conductivity, thermal expansion coefficient. If you see and compare, silicon is the best materials. It has the all the properties, and other thing is it has very good thermal native oxide, silicon dioxide, which make it most suitable for the microelectronics and the MEMS applications. So silicon, conclusion is that silicon is an excellent material from the mechanical point of view, and no other material can replace it. Other material are coming, but they are not abundant. Silicon is abundant in the nature. Like other germanium also, and other silicon carbide or gallium nitride. First, to make them difficult, then they are not available. They are very costly. And it is
The silicon wafer is there, it is around like 3,000 rupees cost, and if same size silicon carbide is like a 4 lakh rupees.
yeah, same way for that is the yeah, very costly,
Very costly.
very costly. So therefore, and if you go for gallium nitride also, that will be cost very high. So silicon is the very low cost, therefore easy to use, and everything is driven by the economy. If you buy the thing which is low cost. So we use the silicon crystalline properties. We know it is a cubic, which is the interpenetrating 2 FCC lattice in the diagonal 1 by 4 directions. You know that it has the planes 100, it has the direction also 100, it has the different planes in the different directions, and we make use of them as per the requirements. We do the processing, we do the lithography, we do the micro machining, we deposit some layer, we pattern it, or we lithography, we etch it. Standard wafer we can use, or we can SOI wafers we can use. We can do our device using the surface micro machining or bulk micro machining as per our requirement. You see the process here, we taken the substrate and we deposit thin film and we done the lithography of it, and we pattern this photoresist. After doing the patterning, we done the etching of it. See, it is etched part here. Then deposition we can do by many things. Epitaxy we can deposit, oxidation we can do, sputtering, evaporation, CVD, sol gel, bonding, silicon fusion bonding, or any other process we can deposit the layers. We can do the patterning by doing the etching. We can do a wet etching, we can do a plasma etching, we can do a dry etching, we can do other kind of etching. Etchings, we have the profiles in the silicon. If it is wet etching, it's like this. It is dry etching, it will be like this. It is the anisotroping, means direction dependent etching, it is like this. It is anisotropic plus dry etching, it is like this. Which is the best? This one is the best, right? Isotroping, it will etch every directions. You see here, this direction is in this direction it is etching, this direction also etching. And anisotroping means it's direction dependent etching, only one direction. Yeah.
It means we want an 54.7 degree angle. It means it is by the isotropic. It depends on the direction. As per our requirement. If you want to generate a color like this kind, we will generate with the isotropic.
Once on the chemical, one plane it is etching, other do not allowed. It's direction dependent etching. Like you see here, etching is done, one masking layer is there, then it is dipped in the chemical, so the etching is done like this. If it is a microscopic image, the trench will look like this from the top side, right? So it is in the silicon wafer, and total thickness of this nearly 400 micron, 0.4 mm. So it is a, we can do a dry etching also, deep reactor ion etching to make the sensors using the SF6 gas, silicon substrate, one masking layer utilized here, and we can make the very fine structures of the good aspect ratio of like this. Okay, this is possible using the deep reactive ion etchings. So the unique processes are developed to make these microstructures at the micron level. So we can do a sensing or actuation, how to actuate, apply F and then sense. So actuation can be thermal, piezoelectric or capacitive. Thermal will give me a thermal expansion, piezoelectric will give me charge, force, and capacitive will give me electrostatic force. Sensing also I can do in this. Piezoresistive will give me a stress, that will give the resistance change, and I will measure it electrically. Similarly, the piezoelectric will give me the force, and that will give the charge. I can capture the charge and measure it. The capacitive will give the capacitance variations. Similarly, we can have a capacitance sensing or actuations. We can use a parallel plate capacitors or IDT kind of capacitors. We done one project on the formaldehyde sensors, especially for the formaldehyde is one of the preservants, and formaldehyde. If you see these fish who use fish, they actually it is coming from the coastal areas, right? And it will reach. It will take 1 week to reach here. By that time, it will be not usable. Right? So what they do, they preserve it. They will apply some formalin solution on it, so it will look fresh. But it is formalin is a very toxic, cancerous. So therefore, if you can check the fumes of formalin in it, you can tell that some formalin treatment is given on it, so that you can tell it is not usable and don't use it. So there was need of formalin sensor, especially for these fish products. So we done one project and we developed the formaldehyde gas sensor, and our gas sensor was able to detect the 1 ppm of the formalin gas solutions here, and we one of our students done this work and then the formalin sensing of the 1 ppm formalin solutions at the using the heated metal oxide semiconductors. Other project we done on the piezoelectric based devices. Piezoelectric materials, we know there are like quartz, one of the materials. We can have aluminum nitride, we can have zinc oxide or PZT. The coupling coefficient is a measure of the coupling, how much energy in the electrical form can be coupled to the mechanical form. So that is called the coupling coefficients. So we know that the PZT has the highest coupling coefficient and the quartz has the lowest coupling coefficient. If we'll see the piezoelectric material like zinc oxide or aluminum nitride, they have a woodsite structures. But depending on their configuration, they can be of rock salt or zinc blend, but they are not piezoelectric because they don't have the lack of center of symmetry. Lack of center of symmetry in the woodsite, therefore they are piezoelectrics. You can see a unit cell of this woodsite zinc oxides. So it is your A and B dimensions are 3.25 angstrom and C is 5.2. So C by A ratio is maintained and therefore it is the polar materials. So woodsite, the tetrahedral coordination, polar symmetry along the hexagonal axis, and it is a polar which has the zinc phase 001 and the oxygen phase 001, C axis oriented. The polar phase possesses different chemical and the physical properties, and the polar phase possesses a slightly different electronic structure to the other three phases. The cubic phase do not have the piezoelectricity. If you'll see the properties of the zinc oxide, its crystal structure is hexagonal and its lattice constants are given for the C-axis orientation. Band gap of it is nearly 3.3 electron volts and it has the piezo coefficient of 12 picocoulomb per Newton, D33. In fact, this material we developed and utilized for our acoustic sensor applications. So this was the one of the device we developed on the silicon wafers. You see here, and what we done the oxide on it, then the bottom electrode on it, then the piezoelectric layer on it, then the top electrode on it. So this make a resonator. We'll understand how it is working as a resonator. But this is a very high quality factor resonator based on the piezoelectric material. Your D is equal to lambda by 2. And it is used in the filters and the reflectors operate at the very high frequency up to the 10 gigahertz. It's providing you better performance and the small size and low cost. If you'll see what is the piezoelectricity, if I'll press the materials, charge will develop on its surface due to the lack of center of symmetry. Due to its movement, the piezoelectricity concept that the anions and the cations moving in the opposite directions due to the influence of the mechanical force. And electric dipoles are generated due to the shifting of these anions. And the device we developed here, the thickness is lambda by 2. Okay, lambda is the wavelength of it, and it's relies on the piezoelectric effect. How it is working? Through this, we apply a AC electric field across this resonator through this supply voltage. Okay, AC supply voltage. When you apply it, this actuates. Application of the external electric field and this give mechanical stress to the bulk of these materials and the acoustic waves are generated. And acoustic waves are reflected back from the air interfaces and they confine in these mediums. And we propagate in the applied field direction and the reflect off from the air interfaces. This provide me a very high quality factor resonators, and resonance frequency is decided by the thickness of this layer stack. Thickness of zinc oxide plus aluminium. This will provide me a thickness of the resonator that will give me the resonance frequency of it. This basically relies on these constitutive relations. T is equal to Cs, we know the Hooke's law, but if you minus E into E, which shows that it is a Hooke's law, modified Hooke's law, includes the emergence of stress associated with the presence of the external electric field due to the dielectric piezoelectric effect. And second equation is the inverse piezoelectric effect, creating a electric displacement when a strain is produced in the materials, where E is the electric field, D is the displacement, C is the stiffness, permittivity, and the piezoelectric constant. These are the various material properties we utilize during our design process. We do the COMSOL simulation of it using a COMSOL multiphysics. We do the resonance and the anti-resonance study. This is resonating at the 1.1 gigahertz resonance frequency. So these are the deformation plots of it. How we do fabricate it in our clean rooms or in our foundries? We have in Siri Pilani, we have a mini fab, and where we do these process. See here, we start with the silicon wafers and we do the thermal oxidation of silicon dioxide, then the patterning of this platinum electrodes. These on the single wafer there will be more than 300 devices. Then second step comes the piezoelectric layer deposition. You see here, this layer is deposited and we done the patterning using a photolithography process, standard semiconductor process. Then the next step comes, then platinum layer again deposited and the circuit is made like this. Then comes the release of it. Then comes the backside etching of it. So these are the processes regularly we do to develop these electronics resonators. If we'll see in the lab, how does the wafer looks? Seeing the color of the wafer is very important. Seeing the color of the wafer, we can tell what is the layer on it. We'll see now. It is simple silicon from the back side. But here you can see some colors. There.
Greenish color.
Yeah.
Actually, initially it is like a bluish one.
Yeah.
After the processing,
Color changes. We'll see here, this some greenish looks, means some silicon dioxide layer is there. And silicon dioxide color changes with the thickness. If we'll increase the thickness,
more dark.
yeah. And if it is silicon wafer, silicon dioxide wafer, I can make a difference. Silicon dioxide is hydrophilic and silicon is hydrophobic. If I'll dip in the water, I can make the difference. So you see the silicon dioxide, it's some violet color. I done the lithography, then this patterns comes, and after etching of it, its window will look like this. Here you see the wafers are oxidation done at the high temperature, 1100 degrees Celsius, very high temperature. So this just to give you a feel how does the wafer looks after every processing. You see the wafers, some cavities and patterns are made here. Okay, and then the cavities look like this under the microscope. Then the some gold layers or some are deposited and then the patterning. Then the lift-off was done. Then you see the zinc oxide deposition. 3-inch wafers at a time we can deposit. And you can see the plasma color. Then the lithography done, zinc oxide patterning, zinc oxide etching. We do 6 wafers in a batch. Then the deposition of titanium gold, then the lift-off process, and the resonator is ready on these wafers. And finally, on the wafer level testing we do. Okay, so this we do the processing of it using the wet etching of it. We do using the these chemical solutions. We do many studies like X-ray diffractions and stress measurements and things we do regularly to make the device more robust and reliable. So stress engineering done and single phase materials are made. These are some of the pictures we made of these resonators. Looks like this, active area of it, and pentagon shape resonator active area like, and it is measured using the LDV laser Doppler vibrometer. The performance was measured, its actuation. Now that it was diced and packaged into this form, and its scattering parameters S11 and with the frequency was measured using the VNA vector network analyzer, and performance was analyzed. And this actuates also. When I apply a AC field, it is a live result. You can play also this, it will actuate. Click on this, it will do a movement. You see this, it is the active area, and it is piezoelectric. When I apply a AC field across it, it is actuating. Actuating means the membrane is going up and down, doing a, due to the apply voltage, it is doing mechanical actuation. Okay, and its performance at a given frequency is measured. So single device, it is of a diameter of equal to our hair diameter, 100 micron. You can see this device is so small, one device is equal to our hair diameter. So small device. Its performance is measured, its impedance for the frequency resonating at the 1 GHz frequency. It is measured using the vector network analyzer. So this electronic product we developed in Siripilani, one of the project. Then we do some other measurements also of this, its magnetic performance, its sensing performance, and some of the calibrations of it. Some of the hysteresis loops of the magnetic materials we measure using. Processing already we discussed. Some of the we utilize it for the magnetic sensor applications by integrating magnetic layers, and we see the response here when we have no field, when we have with field. So there was shift in the resonance frequency. Then we do the modeling part of it, and we do the MBVD Butterworth model we fit, and we simulate the experimental measured data we match with the simulated data, and we extract this equivalent circuit parameters. So with field and without field, we do the MBVD modeling part of it using the ADS, Advanced Design System Electromagnetic Simulator. The S parameters and the capacitance measurements of this was for the different resonator. The electric capacitance was the 0.3 picofarad for this, and resonance frequency was 1.65 gigahertz. Also we done some mass sensor work of this using the micro cantilevers fabrication process, and we done the stress engineering of it. Stress means we done the silicon dioxide, we done the zinc oxide deposition, and the stress profile was measured. Means my device should be reliable and repeatable. So I have to do a stress engineering so that device can be made better. These are some of the zinc oxide deposited and their stress after etching. How does the etching after etching of zinc oxide? How does the profile looks? The profile makes some angles with your underlying layer, and that was measured here. And to improve the step coverage. These are also various micro cantilevers made here. The microstructures was made here. It is a single microstructure. These are the area of microstructures, and these are the 5 micro cantilevers of the different dimensions. Then we done the frequency with the cantilever length. Means their length was varied and their frequency was, resonance frequency was measured. So we can see a data here that as we increase the length of the micro cantilever, its resonance frequency decreases. Similarly, I monitor the deflection of the end of the micro cantilevers, which we measure using the laser Doppler vibrometers, and we do the deflection measurement with the DC biasing voltage. We actuate the micro cantilevers and we measure the deflections. Some of the LDV measurement results here for the various length of micro cantilevers. I have a 300 micrometer length, 250, 200, 150 and 100 micrometers. So the smallest micro cantilever has the highest resonance frequency and it provides me the highest frequency shift. So that will give me a better results. So sensitivity of this mass sensor is like this. It is anti-proportional to the length. So mass sensing was better for the lowest length of the micro cantilever because it was resonating at the high frequency, and high frequency will give me high sensitivity. So here we compare the table mass sensing performance of the various micro cantilevers. You will see that the smallest length micro cantilever give me the highest mass sensitivity. Similarly for these you can see here the wafers, 3-inch wafers, and these cantilevers are made on it, and one die you can see it near to the coin. So it is so small, smaller than our this dimension. And if you measure these cantilevers, this cantilever length is 580 micron, means 0.5 mm, length is 0.1 mm. So very small size micro cantilevers are made and using for the magnetic sensing applications. Also we done the stress engineering. Silicon dioxide has a compressive stress and the iron cobalt has a tensile stress. So we done the stress engineering to make the low stress micro cantilevers, and a low stress was achieved using a bilayer combinations. This is the one of the equipment we have in series. It is called the laser Doppler vibrometers. Any MEMS or microsystem movement we can measure using this machine. So it is very good product, and we all these MEMS and microsystems measurement we do using the laser Doppler vibrometers. So this will provide me live results, actuation of the device you have seen. This is possible with this laser Doppler vibrometer. These micro cantilevers were mounted on a piezo disc, and its resonance frequency, you can see it. It is mounted on a piezo disc. Then the piezo was actuated by applying AC signals. Its dimension in the centimeters. We measure the amplitude versus the frequency. It is resonating at the nearly 25 kilohertz. Phase was changed there. So resonance and phase was measured here, and this was utilized for the magnetic sensing applications. So magnetic output voltage was measured with respect to the applied magnetic field. We find that there was a millivolt range magnetic signal was obtained. And we do the fabrication using a standard MEMS and microsystem processing, like the silicon wafer, their oxidation, their electrode deposition, then the zinc oxide or some metal layer depositions, iron gallium depositions, pad open, and the magnetic sensor final fabrications. One of the magnetic sensors we developed in Sri Pilani, that is 3-inch wafers. There are many sensors in it, and then we packaged in the sensor, and it's looks like this after the 24-pin package, and it give me output millivolt range signal when you apply magnetic field to it. This is also a magnetic sensors, and can actuate it. It actuates like this when we apply a AC signal across it. These are some of the FEM and the stress analysis. Before doing the actual experiment, we do a COMSOL or Coventer studies, and we do the analysis. Some of the nanorods and nano dimension figures were made, and the structures were developed, and nanorod signals was obtained. Z nanowire based energy generator. In Siripilani, we have the major facilities like the sputtering. We have the mask making facilities to make these devices. PECVD plasma enhanced chemical vapor deposition. We have etching setup, metallizations, mask aligner, reactive ion etching, laser dicing. We have X-ray diffractometer, vibrating sample magnetometers, IV characteristics, PL mapping, scanning electron microscope, stress measurements, vector network analyzer, RF probing, DEC tech. So it is a kind of many foundry facilities are there. So we learn about that today's the fundamentals of piezoelectric MEMS and microsystems. We learn about the current trends in it. We learn about the Indian semiconductor missions, acoustic wave resonators and filters. We getting support from the various agencies to doing these experimental works from the various sponsors we get. To make in this presentation, I utilize the various resources and the references are listed here. Thank you for your attention. Any questions?
You just show us a Smith chart. So actually, what kind of parameter we expect from the Smith chart, and how to draw a Smith chart for sensors?
It was drawn for a resonator.
Resonator.
Yeah. Smith chart give me a reflection coefficient. Okay. Right. So Smith chart was plotted here for a resonator, which is the piezoelectric based resonators. And a S11 parameter, if I'll measure the S11 decibel versus frequency. But Smith chart will give me a real and the imaginary part. And I can make out that device is either capacitive or either inductive or resistive. So I can make the difference. And I can make whether it is the impedance or admittance or the kind of parameters I can.
Because actually, we initially when we study about the Smith chart, we draw a Smith chart for a pi 3.14, what is a kind of the same kind of a Smith chart will draw for a pi value of pi.
3.14.
3.14, and there's a
so it is a real part. It will come on a horizontal axis. Right.
Thank you, sir.
Excuse me, sir. I think there are the many fabrication methods, right, sir? One is bulk micro processing, right, sir? Bulk micro surfacing method, and second one is the photo lithography method. Okay, right, sir? So which one is better than the other?
See, surface micromachining is more preferred because the cost is less and device performance is better and device packaging is better in the surface micro.
Sir, actually, sometimes we are using the photolithography.
Yeah.
Why? It is better.
Lithography we use to make the patterns. Suppose I made a one layer on it, continuous layer on it, on this wafer, and I need some pattern of it. Right? I don't need everywhere. I need at specific portion. So how I'll pattern it? I have to do lithography. Lithography will provide me a fine features. Fine features you can see here. Those possible using the lithography.
Thank you.
Thank you.
Thank you, sir, for your enriching session. Now, I would like to request VP coordinator, Mr. Rajesh Singh Shekhawat, to honor our distinguished speaker with the token of love. Sir. Thank you, sir. Thank you, everyone.